To achieve maximum performance and minimum emission levels, a spark ignition engine requires the highly compressed air-fuel charge to be ignited at a precise time. For correct ignition timing, each cylinder should receive spark at the plug's centre electrode as the piston nears the top of its compression stroke. This is where the cylinder pressures are at their peak. Ignition here results in the greatest torque produced by that cylinder. But it's not all about igniting the mixtures at the correct point in the piston stroke. The time it takes to burn the compressed air-fuel charge must be taken into account. Generally, around 3 milliseconds is required for ignition of a stoichiometric air-fuel mixture. Let's have a quick look at the ignition process relative to crankshaft position and speed. At idle speed, with the perfect air-fuel ratio, the crankshaft moves through 18 degrees of rotation during an ignition event. With the same air-fuel ratio and an increase in crankshaft speed to around 2,000 revolutions a minute, the ignition event lasts for approximately 36 degrees. Again, at higher speeds, the ignition event lasts much longer, in this case around 90 degrees of crankshaft rotation. As can be seen, the greater the crankshaft speed, the further the piston travels during an ignition event. This means the ignition firing point would need to be advanced for higher and retarded for lower crankshaft speeds. Unfortunately, not all cylinder charges take the same time to burn. The time required alters with changes to the air-fuel ratio. Rich mixtures ignite relatively quickly, while a lean mixture takes longer to burn. An engine under hard acceleration requires the ignition timing point to be advanced to allow for the higher crankshaft speed. But due to the enriched cylinder charge, the total advance will be less than maximum. When the desired engine speed has been reached and the throttle plate angle is reduced, the ECM leans the fuel mixtures off to cruise ratios. At this point, the engine speed is still high, so the ignition advance due to crankshaft speed remains high. But allowances must now be made to the ignition timing for the leaner air-fuel mixtures. More ignition timing advance is required to burn the lean cylinder charge. The total ignition advance will now be somewhere close to maximum. The perfect ignition point is dependent on engine speed and load. This is due to the fact that as these conditions change, so does the charge mixture within the cylinder. Early ignition systems had different methods for adjusting the ignition timing to suit varying engine speed and load conditions. A set of centrifugal weights attached to the distributor shaft act as the engine speed advance mechanism. Expansion springs hold these weights in the retracted position until distributor shaft rotational speed creates sufficient centrifugal force to overcome the spring retaining pressure. Movement of these weights act on the distributor cam, causing rotation in the advanced direction. This movement opens the points earlier in the cycle. The higher the engine speed means more movement of the centrifugal weights, so therefore greater ignition advance. As the engine speed drops, centrifugal force is lower. This allows the retaining springs to pull the weights to their rest position, reducing the ignition advance. The strength of the springs plays a critical part in how far and how fast the weights move, therefore determining the amount of timing advance. It's very common to have two different strength springs. One weight will begin to move out earlier than the other, allowing a more progressive advance. The amount of advance allowed by the weights can be checked with a timing light and increasing engine RPMs. The timing mark will be seen to advance. The centrifugal weights are crankshaft speed sensitive only and do not affect timing for differing load conditions. When the engine is cruising at part throttle, it is common for the fuel mixture to be leaned out for maximum fuel economy. Because a lean mixture is harder to ignite and takes longer to burn, it must be ignited earlier. A vacuum advance unit is used for this purpose. The vacuum advance unit housing is divided into two sections by a diaphragm, which connects via a linkage to the base plate of the distributor. The base plate secures the ignition points and has limited rotational movement within the distributor housing. The diaphragm is connected to a ported vacuum source on either the carburetor or throttle body. Vacuum is only applied to this port when the throttle plate angle is between approximately 25 and 75%. Vacuum acting on the diaphragm will draw the base plate against the direction of rotation of the distributor cam. This opens the points earlier in the compression stroke, advancing the ignition timing. When the throttle angle changes to either wide open or closed, the ported vacuum is reduced, relieving the pressure acting on the advanced diaphragm. The diaphragm return spring pushes the linkage and base plate to its home position, retarding the ignition timing to its base position. Although mechanical and vacuum advance systems have been used extensively in distributors with electronic trigger systems, they are still mechanical by nature and are subject to wear, tear and ongoing maintenance. Electronically controlled spark advance systems have to balance a number of sometimes opposing objectives: vehicle emissions, engine power output, fuel consumption and engine life. The vehicle's ECM now controls all ignition events and is programmed to respond to changes based on engine sensor data. Most base ignition maps have the same approximate shape. As the engine RPM increases, the ignition advance increases. As engine load increases, the ignition timing point must also increase. This timing curve is very linear in shape until the engine reaches high RPMs. At this point, the curve levels off. This is because from here, the ECM does not use feedback from the knock sensor. This is for a very good reason. It is difficult to differentiate between knock and normal engine noise at high load and high engine RPMs. These newer ECM controlled systems are adaptive, meaning they continuously adjust the ignition timing advance in order to best meet the engine operating requirements. Based on sensor input data, the base map can be corrected to suit different fuel qualities, pressures, altitudes, and even valve timing wear. The goal of any ECM spark timing system is to add the highest proportion of advance wherever possible. It does this by starting with the base timing point and slowly increasing the available advance while monitoring the feedback from the knock sensor. Based on its presence or absence, the ECM will then slowly decrease or increase the timing point until knock sensor feedback is within acceptable levels. This process is continuous, meaning the engine is able to meet a wide range of operating conditions while maintaining peak performance with minimal emissions. Any corrections made are recorded to the ECM's long-term memory. This is known as coarse ignition learning. Coarse ignition learning is very similar to fuel trim correction. Once the coarse corrections have been made to the base ignition map, fine ignition learning is then able to be performed. The ECM is then able to make more precise ignition adjustments to meet the wide range of operating conditions. Dwell is the period of time that the ignition coil is switched on, or it's the length of time that current is allowed to flow through the primary windings of the ignition coil. In an old Kettering system, current only flows when the points are closed. In modern systems, it's the time the control module activates the primary winding transistor. Ignition coils produce their energy from the collapse of a magnetic field. Correct dwell allows this field to reach its maximum strength within the design limits of the coil. Correct dwell control has a direct effect on current level and therefore the energy produced in the secondary coil windings. Common ignition modules have a sophisticated closed-loop control of dwell. These modules monitor the coil current and adjust the dwell to ensure a specified target level of around 7 amps is always reached. This approach caters for varying engine RPMs, temperature changes, battery or ignition voltage fluctuations, and so on. Should the current rise above the target, then the module's electronics will limit the current flow to the power transistor. When viewing the current trace, this can be seen as a flat section on the top of the pulse. This point is when the ECM sets the dwell. Most ignition coils that have the drivers built in have some form of overcurrent protection. Some even have thermal protection that will reduce their heat dissipation temporarily until it's under control. Modern ECM ignition systems are complex yet extremely reliable compared to older Kettering types. As these systems get old, failures will occur. Understanding how they operate will prepare you for when this occurs. Thanks for watching.